The dimensions of the universe far exceed our imagination. Although we are able to quantify the dimensions of the gigantic structures of the cosmos, the corresponding values are sometimes very abstract and not very tangible. However, this scheme can also be applied to the exact opposite case. For some time now, researchers have been eager to unlock the smallest secrets of the universe. And in fact, the CERN researchers recently achieved a real milestone: building blocks of matter. Before we go into more detail about the exciting discovery of the CERN scientists, we should answer a short question in advance. What are quarks? Well, they are nothing other than those elementary particles that embody the fundamental building blocks of all matter. However, they are not physical singles. In truth, quarks always come together in coupled bonds called hadrons. This also includes protons and neutrons, or in other words, the components of atomic nuclei. Within the standard model of particle physics, quarks enjoy an exceptional position. They are the only elementary particles that are subject to all four fundamental interactions. In turn, experts distinguish between 6 types of quarks. These so-called flavors can be divided as follows: up, down, charm, strange, top, and bottom. Protons and neutrons, for example, consist of up and down quarks, or in other words, those quarks that have the lowest mass. Their heavier counterparts, in turn, are found only in extremely short-lived hadrons, such as those formed in modern particle accelerators. For a long time, however, quarks were known only as pairs of 2 or as trios. Excitingly, this list has some new entries thanks to recent research. We now also know of the existence of tetraquarks, pentaquarks, and even hexaquarks. It seems as if more and more new, exotic hadrons are being detected. In fact, experts even compare the current research period with the groundbreaking era of the 1950s, when scientists encountered a veritable particle zoo that was to become the foundation of our current standard model. The newly discovered quark compounds impressively demonstrate to us what processes really take place in secret. And as became known a few months ago, this successful search for clues continues unabated. The corresponding discoveries were recorded in the context of high-energy proton collisions in the Large Hadron Collider at the CERN Research Center. Some of you will certainly remember the controversy that the commissioning of the particle accelerator once triggered. At that time, there was talk of the creation of microscopic black holes that would plunge our planet and its inhabitants into ruin. Fortunately, this apocalyptic scenario has not materialized, and instead has given way to a scientific success story. 3 new particles. After the scientists analyzed the captured particle tracks, it was clear that they had just encountered the signature of 3 previously unknown particles. The first discovery concerns a pentaquark. As its name suggests, it is composed of 5 quarks, including 2 heavy charm quarks. At the same time, the discovery becomes the first known pentaquark to contain a strange quark. In order for a discovery to be verified, it must reach a significance of 5 sigma. In this case, the value was as high as 15 sigma, which means that the find is considered unequivocally confirmed. According to the experts, the detected pentaquark could help us understand the background of the particle compounds more precisely than ever before. So far, we do not know whether the quarks in such multiple couplings are even connected, or whether it's rather a loose association of pairs and trios. In addition to a discovery from 2019, the more recent finding suggests that the latter is the case. This emerges from the detected mass, which, at 4,338 mega-electron volts, is on the borderline of baryon-meson production. Thus, the pentaquark could be composed of a meson consisting of a quark-antiquark pair and a baryon composed of 3 quarks. In the second discovery, we are again dealing with a 2-pronged finding: a neutral tetraquark and its doubly charged tetraquark counterpart. In fact, this is the first time in the history of research that this type of particle appears in a pair compound. Both components have a mass of about 2.9 giga-electron volts and are composed of a strange antiquark and a charm quark. In addition, one quark has an up antiquark and a down antiquark. The other, an up quark, and a down antiquark. Especially interesting, currently, experts assume that the particles embody so-called isospin partners, which means that they represent two states of a quantum mechanical system. However, it's still unclear at present whether other partners of this type exist and what the details of the couplings are. With significances of 8 and 6.5 respectively, the confirmation hurdle was easily cleared in this case as well. At present, however, the exciting work of the particle researchers is still at its beginning. In the best-case scenario, a unified model of exotic hadrons will be available at the end of this research path. Furthermore, the in-depth investigation will also help to significantly deepen our knowledge of particles such as protons and neutrons. Gigantic megahalos. From small-scale sensations to outsized discoveries, recently, astronomers recorded a groundbreaking find while studying galaxy clusters. According to our current research, galaxy clusters embody the largest gravitationally bound structures in the cosmos. Here, thousands of star worlds move around a common gravitational field. These gigantic structures are completed by dark matter and countless gas clouds. All in all, clusters have up to 1 trillion solar masses. In view of these breathtaking compounds, however, one question arises: how do galaxy clusters form in the first place? Most researchers agree that clusters are the result of galactic mass collisions. As the galaxies collide, the interaction of their particle currents and magnetic fields causes electrons to accelerate to near the speed of light. As a result of the braking effect of their surrounding fields, the particles then emit energy in the form of radiation. These signatures reveal themselves as radio halos in the center of the structures. In order to take a closer look at the radio emission of clusters, scientists at the University of Hamburg targeted 310 massive clusters with the help of LOFAR. This is a network of 4 radio telescopes located at different sites in Europe that combine their signals into a single signal. Astonishing observations. In the course of the analysis, 4 clusters ultimately stand out in particular. In addition to the expected radio halo in the center, they also contained amazingly large fields of diffuse radio emission. The volume of these structures exceeds that of the radio halos, sometimes by a factor of 30. Furthermore, these so-called megahalos have extensions of up to 10 million light-years. However, these enormous dimensions are not the only point in which the structures differ from their known halo counterparts. The original assumption that they are simply larger versions of conventional radio halos could not stand up to more detailed investigation. In fact, the growth of ordinary radio halos is limited due to the rapidly decreasing energy of the electrons in the center. This also emerged from the current observations. According to them, all analyzed structures have 2 different components. On the one hand, there is the brighter area in the center, which is dominated by the radio halo, and whose brightness decreases the further one moves away from the heart of the galaxy cluster. On the other hand, there is a less bright, but much more extended region. Especially puzzling, in contrast to the radio halos in the center, the intensity of this component does not decrease in the outer regions. Rather, the brightness of the megahalos remains largely the same over distances of more than 1.6 million light-years. These structures also differ significantly from known radio halos in terms of frequency spectrum. All these differences thus suggest the pressing conclusion that the megahalos are independent structures formed separately from the radio halos of the center. On the basis of this, then, the question arises: what is the mechanism of formation underlying the megahalos? In this respect, the models of the experts say that the radio emission must go back to the intercation of electrons and magnetic fields. Or in other words, cosmic oceans of relativistic electrons must also exist behind the outflows of the radio halos in the center. However, at present, it's still completely unclear how the particles there obtain their energy. No less puzzling is the fact that the intergalactic medium decreases 5-fold in the foothills of the clusters, and yet the radio emission remains largely constant. Either the intensity of the magnetic fields in the outer regions must increase, or the energy density of the hot gas But it's also possible that fluctuations in the galactic structure, such as the entry of matter into the clusters, are what help the megahalos grow so large. A dimensional gate has opened. On July 7, 2022, at 5:18 a.m., a shocking discovery was made. A mysterious crack appeared in the Earth's magnetic field. The crack appeared out of nowhere and remained open for a full 14 hours. The anomaly allowed solar winds to flow into the Earth's magnetic field, causing strong geomagnetic disturbances and possibly much more. How did this crack suddenly appear, and what does it have to do with the tests at the Large Hadron Collider in Geneva? Researchers were quick to come up with an explanation, claiming that the crack in the Earth's magnetic field was due to a unique phenomenon called the correlating interaction region. CIR is a phenomenon in solar physics that results from the interaction of different solar wind streams. The solar wind consists of charged particles emitted from the sun into space. These particle streams never move uniformly in all directions, but have different velocities and densities. Near the sun, sometimes several of these solar wind streams meet and overlap, forming very large plasmatic formations that exert a special effect on the Earth's magnetic field. Unlike normal plasma streams, they can apparently tear a real hole in the Earth's magnetic field. CIRs have not yet been researched sufficiently to be able to say what consequences this really leads to. Interestingly, 3 new exotic particles were discovered in the Geneva Collider at exactly this time, including a new type of Petter quark and the first pair of tetraquarks, which include a completely new tetraquark. Scientists claim that the Large Hadron Collider deep underground is absolutely safe and does not interact in any way with the outside world. But can this be true? After all, we are moving here in the subatomic realm, exactly where matter becomes nothing more than oscillation and rotation with gigantic empty spaces between tiny particles. Quantum mechanics have long pointed out that the building blocks of our matter are multidimensional, that particles of light are in multiple places at once, and even transcend the barriers of time and space. So how can researchers claim that none of the particles being researched at the controversial CERN facility are getting outside or interacting with other dimensions of the universe? Officially, 70 new hadrons were discovered by the CERN community during the series of tests. These are subatomic particles composed of quarks and held together by the elementary force of the strong nuclear force. However, critics of the facility claim that CERN is doing far more experimentation in depth than is officially known, and that is what could put us all at risk. There have been frequent speculation that the organization is trying to create black holes, unwittingly or deliberately opening gates to other dimensions we cannot control. Warning from an extraordinary child. Max Laughlin is a highly gifted boy who, out of nowhere, has an extensive knowledge of quantum physics and the nature of our reality. He warned in a video that CERN had destroyed the old universe when it resumed operation of the facility in April 2022. He claimed that there had been an original timeline, but because of the experiment, an anomaly had immediately occurred, catapulting us into an infinite number of parallel universes. According to quantum physics, however, there would be nothing too unusual about this, because if experiments like Schrödinger's cat and Wigner's friend are right, we are all constantly moving through a multitude of universes with our decisions and measurements of consciousness. Max Laughlin, however, believes that the experiments have shifted humanity as a collective, along with the planet, into another dimension. Most of us have been unaware of this. Let's hope this new level of reality is a good one. No black holes, no dangerous experiments. A physics professor from the University of Buffalo involved in the testing explained that the collider, or any technology for that matter, can access black holes at this time because there are still certain limitations. However, it's known that minor breakdowns in the space-time continuum have occurred in Geneva that are similar in nature to black holes. When this became known, it led to protests against CERN, with a group of people demanding that the particle accelerator be shut down. Again and again, strange weather phenomena occur around Geneva, and local residents report perceptions that cannot be explained by normal means. Several professors and renowned researchers have also spoken out and reaffirmed their confidence in the Large Hadron Collider. The main goal of this current run of tests at the particle accelerator is to find out more about a mysterious fifth force of nature that researchers believe exists. This fifth force, if found, would completely change the dynamics of particle physics. Only no one has really seen or measured it yet. Critics of the facility are up in arms about it again. They claim that the researchers are playing God in the depths of the Earth, and that no one can really foresee the true consequences of these experiments at the moment. The Large Hadron Collider. The Large Hadron Collider, LHC for short, is the largest and most energetic particle accelerator in the world. It took 2 decades to build, accompanied by protests and criticism. While more than 10,000 international scientists, hundreds of universities and institutions, and 100 countries were working on this revolutionary project, ordinary people in the Swiss city of Geneva feared for their peace and safety. Despite petitions and complaints, the Swiss government and international funders pushed ahead with construction of the more than 7.5 billion euro facility. The particle accelerator is located between 100 and 175 meters below the Earth's surface. Above it are residential areas, supermarkets, kindergartens, and roads. Those who don't know about the existence of the facility imagine they are in a completely normal city. But the people of Geneva are increasingly unable to forget what is going on there in the depths. The actual facility is the 27-kilometer-long tunnel in the form of a ring consisting of superconducting magnets. Special acceleration structures massively increase the energy of particles. 2 beams of particles travel clockwise and counterclockwise, respectively. At a speed close to the speed of light, the particles collide. Only through this ultra-fast collision do the particles become measurable. They interact with each other or decay into still smaller particles. The main components of protons are quarks and gluons. Quarks, being subatomic particles, are very unstable and usually decay in a fraction of a second, while gluons are the mediating force. The entire collision is detected by detectors inside the accelerator, and the data is sent to a network of computer systems. From the decay and behavior of the particles during the collisions, researchers hope to learn more about particles far below the limit of what is visible. No human has ever seen even a photon or an electron in isolation with their own eyes. Researchers only know of the existence of these particles because they can observe their effects and behavior. The first collision in the Large Hadron Collider was performed 2 years after the accelerator was completed in 2010. Prior to that, similar tests were conducted at a predecessor facility, but the prototype particle research facility was far less energy charged. The tests from 2010 took place at a combined energy of 7 tera-electron volts, which was nearly 4 times higher than any previous and comparable test series. But that still wasn't enough to produce ever smaller particles. Further upgrades increased the intensity of the combined energy of 13 tera-electron volts to produce. In 2018, the plant was unexpectedly shut down. Local residents linked the plant's shutdown to a strange weather phenomenon that had appeared over Geneva during the summer. In addition, people in Switzerland and neighboring regions in southern Germany and France reported strange events, and seismologists measured many smaller earthquakes. But all of this is officially said to have nothing whatsoever to do with the shutdown of the facility. For 2 years, the LHC remained off. Then, in 2021, the first test runs went through again, this time with a maximum beam energy of 6.8 tera-electron volts per beam. The new full test series is expected to last until 2025. Higgs boson, the God particle? Over the years, the Large Hadron Collider has solved some big mysteries, such as the Higgs boson particle. Before the collision in 2012, the Higgs boson particle and the Higgs field were only a theory, as researchers could not detect it even after numerous experiments. After further upgrades to the collider, the Higgs boson was finally detected. In the course of this series of tests, the researchers also searched for more information about dark matter and so-called ghost particles, or neutrinos, which are similar to electrons, but carry no electric charge and are created in the depths of stars. The Higgs mechanism is a theoretical concept that explains how particles acquire their mass. The Higgs field permeates all of space and imparts mass to other elementary particles as they move through the web. Without the Higgs field, most particles, including quarks and electrons, would have no mass and continue to travel through space at the speed of light without taking on a solid form. The field is thus instrumental in the formation of matter, and thus a basic structure of the universe. The discovery of the Higgs boson was announced in 2012 and was a great success for particle physics. At that time, there was more frequent talk in the media of the God particle. Far stranger than the God particle are strangelets, hypothetical, exotic matter objects made of strange quarks. Strange quarks are one of the 6 directions of quarks, the fundamental building blocks of hadrons, which also include protons and neutrons. Unlike the light up and down quarks that make up ordinary matter, strange quarks are heavier and more unstable. The idea behind strangelets is that they could represent a collection of strange quarks in a stable state. They could form when enough energy is applied to create strange quarks and keep them in a larger system before they decay. Strangelets could also form as a result of a collision of extremely high-energy particles. One of the special properties of strangelets is their stability compared to normal matter. It's speculated that once a strangelet forms, it could act as a catalyst for the transformation of ordinary matter into strange matter. This has led to scientific discussions about whether strangelets could be a potential hazard if they were created in our environment. Experts claimed that a strangelet escaping to freedom from the experimental facilities in Geneva could threaten the stability of the entire universe. On the track of creation with the particle accelerator. The world's largest and fastest particle accelerator is located in Geneva, Switzerland, near the border with France. Thanks to superconducting magnets and proton beams, the Large Hadron Collider can collide particles at extremely high speeds. Now you may be wondering what the point of that is. Well, the problem is that while we humans know of the existence of subatomic particles, we have never seen them. In fact, we have never even seen an atom. These particles are so tiny that even the most powerful microscope on this Earth would not be enough to make them visible. We only know of their existence and can describe them because we perceive their interactions. This is exactly what scientists are doing in Geneva. They are chasing the particles at extreme speeds so that they can study them on the basis of their reactions to each other. This is currently the only way to find out what the building blocks of our world and the entire cosmos are made of. In 2016, the Large Hadron Collider was shut down in a completely unexpected move and was recently put back into operation. The new experiments in Geneva are running with even more energy, and the scientists are setting one record after another in the hunt for the God particle. What's really going on in Geneva? Just before the shutdown, this apparition over Geneva caused horror among the population. The appearance of this lightning twinkling portal in the sky coincided exactly with the start of the Awake experiment in the Large Hadron Collider. Awake is a proof-of-principle experiment to study the use of plasma wake fields, which are propelled by a proton beam to accelerate charged particles. Press spokesman claimed that there was no connection whatsoever between the thunderstorm front, which was presented as quite normal, and the Awake tests. Oddly enough, however, there were several other striking natural events around the world surrounding the start of the experiments. However, the operators of the facility continued to claim that there were no correlations, but critics see it differently. Finally, it became known that not only particles are accelerated and studied in the depths of Geneva, scientists also use the shielded nature of the facility for strange experiments with weather and artificially generated clouds. Ostensibly, the tests are designed to help understand global warming. But critics say experiments like these could wreak havoc on the world's climate. They argue that we still know too little about the connections and interactions and can't be sure that experiments taking place below the ground won't have an effect on the planet's atmosphere. CERN researchers, of all people, should know that there are no boundaries and no distances in the world of particles. Critics once again became alert when the Large Hadron Collider was shut down in 2016 after a major earthquake took it completely by surprise. The world of the smallest particles. Atoms, electrons, neutrons, and protons have been known to the world of science for more than 100 years. But even then, researchers suspected that there were particles even far smaller than these. The quanta are light particles, which were long considered the actual building block of matter. But in the meantime, we know that there are even smaller particles, or quantum is not equal to quantum. Quarks, top quarks, W and Z particles, the Higgs boson, or even the strangelets, which form the building blocks of strange matter, are just a few of the many elementary particles that we know of today, thanks in part to CERN. The discovery of the Higgs boson was frenetically celebrated in 2012. The press even said that the CERN scientists had finally found the God particle in Geneva. With this smallest particle, it should finally be possible to explain all the origins of matter, and at best, we would finally have deciphered the blueprint of the universe. Since this phenomenal discovery, things have officially gone quiet around the CERN facility. Future discoveries have not been shared with the public quite as loudly and conspicuously, and there is supposedly a good reason for that. Dangerous experiments. Deeper and deeper, researchers in Geneva are penetrating the web of the universe and the world of the smallest particles. In the process, researchers have found even stranger and more unpredictable particles and forms of matter. For some scientists, a limit has long been reached in this field of research that we had better not cross. Such voices have long come not only from ordinary people and concerned residents in Geneva, but also from international scientists. If you want to understand matter, you inevitably have to deal with the elements of dark matter and antimatter. And that's exactly what the researchers in Geneva are doing. In the process, researchers in Geneva are said to have inadvertently opened a portal. According to some para-researchers, this had already existed in 2016 when the Large Hadron Collider was unexpectedly shut down. Then it closed again, and with the resumption of experiments in 2022, this gate also opened again. At worst, the work in Geneva will catapult us into another dimension, or we will inevitably move towards a major global catastrophe. Supposedly, we normal people have not even noticed how the Earth has moved to a new level of reality due to the new operation of the Large Hadron Collider. Critical scientists predict that their gloomy predictions will soon be confirmed. The shift in dimensions will be most noticeable in the overlapping of truths and events. These people also claim that the Mandela effect is evidence of this living in multiple dimensions and truths. The effect is named after the former South African freedom fighter and later president, Nelson Mandela. Surprisingly, a large percentage of people around the world assumed Mandela died during his imprisonment in the 1980s. But in fact, the man was released from prison in 1990 and rose to become president of South Africa after the end of apartheid, which he had fought so fiercely against. Some of the people who believed in Mandela's death even claim to have seen the funeral ceremonies on television. Later, they found themselves in a reality in which Mandela was still alive. Psychologists claim that behind this effect was a misinterpretation of the mind. Others, however, think that here two dimensions and realities would meet. Another effect, by which we shall soon notice that we are now already in another dimension, is the appearance of far coarser particles. So, if the scientists in Geneva soon announce to have found such strangely coarse and never before discovered particles, it could become serious. What exactly the dimension change would mean for us, however, even the critics do not know. Maybe Mickey Mouse suddenly appears, Nelson Mandela still lives, or we disappear into a gigantic black hole. At this point, You surely must have some idea, of which you could share with us afterwards. The experiments continue. In Geneva, people either laugh at such dark prophecies or do not take them seriously at all. The scientists here are already fully occupied with their new projects. They are on the track of a mysterious fifth force of nature. Beside the gravitation, the electromagnetism, the weak and strong interaction, there should be at least one more elementary force in the cosmos. This could be truly like the gate to a new dimension. However, this realization would be completely harmless, according to the CERN researchers, and an enrichment for natural science. Neutrinos play a special role in the latest tests. These particles shoot through space in gigantic quantities. In just 1 second, around 100 billion neutrinos pass through every square centimeter of your body. Neutrinos have often been called ghost particles in the past. They are subatomic particles that resemble electrons but have no charge that we can measure or know about. They are created in stars as a result of nuclear fusion. Shortly after the Large Hadron Collider was turned on, scientists rejoiced because for the first time, they were able to visualize a neutrino. We do not yet know what role these particles play in the cosmos. They seem to have a low rate of interaction with matter, yet they are certainly important for some reason. Neutrinos are known to pass through thin forms of matter without difficulty. From 2006 to 2016, researchers took measurements in Antarctica and discovered something outrageous there. The Antarctic Impulsive Transient Antenna, or ANITA balloon for short, was able to measure not only neutrinos coming to us from the cosmos, but also a mysterious neutrino swarm from inside the Earth. The incredible thing was that the swarm had apparently traveled 7,210 kilometers from the Earth's interior. But this is not actually possible. The big question was how particles, which are produced by nuclear fusions, could come out of the Earth's interior. There was an interesting explanation for this in purely mathematical terms. According to this, the neutrinos could have come to us from another dimension. Or neutrinos are able to penetrate thick layers of matter. The discovery alone shows us again how little we know about the particles that CERN scientists deal with every day. Neutrinos from the Earth's interior prove that particles do not stop at thick walls or the possibly limp safety precautions in the Large Hadron Collider. From quarks and hadrons. Before we turn our attention to the exciting discovery that recently spilled out to the public from the ranks of CERN, let's first clarify a fundamental question. What exactly are quarks? Put simply, they are those elementary particles that embody the fundamental constituents of matter. Quarks have the characteristic property of combining to form composite particles, so-called hadrons. These include protons and neutrons, the components of atomic nuclei. In fact, quarks are the exact opposite of singletons. As a result of the so-called confinement phenomenon, these particles never appear in isolation, but exclusively bound. In addition to hadrons, this can also occur in the form of quark-gluon plasmas. A short look at the standard model of particle physics shows why quarks have an extraordinary importance there. According to it, quarks are the only elementary particles which are subject to all four fundamental interactions. Namely, these are the strong and the weak interactions, as well as electromagnetism and gravitation. Basically, the experts distinguish between 6 types of quarks: the up, down, charm, strange, top, and bottom quarks. For example, protons and neutrons are composed of up and down quarks, or in other words, those quarks with the lowest mass. Heavier representatives of these elementary particles in turn only occur in short-lived hadrons, which have their origin in high-energy collisions. This can be the case, for example, in cosmic rays or in particle accelerators, which brings us back to CERN. 3 unknown particles. For a long time, quarks were known only as pairs of 2 or 3. In the recent research past, however, scientists have been able to detect novel particle assemblies composed of more than 3 quarks. The use of particle accelerators has revealed the existence of so-called tetra, penta, and even hexaquarks. It seems that practically every scientific analysis brings new exotic hadron forms to light. According to the CERN scientists, we are living in exciting days. The current research era can be compared to the discovery era of the 1950s and 1960s, when experts encountered a veritable particle zoo in the course of their work. In fact, the discoveries of those days still form the basis of our modern standard model of particle physics. With each new discovery that the experts make in this exciting field, it becomes clearer to us what constellations are really possible in the hidden realm of quarks. One exciting squad, which recently was to be extended by another entry when experts performed high-energy proton collisions in the Large Hadron Collider at CERN. Examination of the particle signatures recorded in the process revealed the existence of 3 previously unknown particles. The first discovery is a so-called pentaquark. As its official name suggests, it's composed of 5 quarks, including 2 heavy charm quarks. At the same time, this discovery represents the first known pentaquark, containing a so-called strange quark. As already mentioned, neither charm nor strange quarks are found in the building blocks of atomic nuclei. According to the scientists, the analysis of the mass could help to understand how the connection of such 5 quark groups is formed in detail. In fact, there are still some fundamental questions to be solved in this respect. We do not know whether the quarks within these assemblies are evenly coupled, or whether it's more of a loose structure between a trio and a pair. Past analyses suggested that the latter is the case, and the recent CERN discovery also seems to support this theory. With a mass of 4.338 mega-electron volts, the pentaquark is at the limit for baryon-meson production. A brief classification: baryons, which include the proton and neutron, are subatomic particles with relatively large masses. Mesons, which are made up of a quark-antiquark pair, are in turn considered to be of intermediate mass. So in the case of the newly discovered pentaquark, the thesis is now that this combination is made up of a baryon of 3 quarks plus a meson. Exotic pair of tetraquarks. But as already mentioned, the scientists found not only 1, but 3 new particle assemblies in the course of their experiments. The second discovery is a doubly charged tetraquark that appeared together with a neutral tetraquark. Thus, for the first time in the history of research, it could be proved that such particles can also appear in pairs. Both the doubly charged and the neutral tetraquark consist of a strange antiquark and a charm quark. Their respective mass is given as about 2.9 giga-electron volts. In this respect, the researchers assume that we are dealing with so-called isospin partners, or in other words, 2 tetraquarks representing 2 states of the quantum mechanical system. But even in this case, we are still far from having deciphered all the background of this exciting particle pair. The questions of whether other pairs of this type exist and how the quarks are connected within this constellation have yet to be answered. In order to get closer to solving the puzzle, it will be necessary to continue tracking down new exotic particle constellations in the future. This exciting research path should one day result in the development of a unified model of exotic hadrons. However, such discoveries are also of great importance when it comes to understanding conventional particles such as protons and neutrons even more precisely. Mysterious Martian mineral. From terrestrial research facilities to the gigantic expanses of space. In 2015, the Mars rover Curiosity recorded a puzzling discovery. Once it landed on the surface of the red planet on August 6, 2012, the rover's mission was intended to answer an age-old question for us. Was or is Mars capable of harboring life? It's possible that the answer to this gripping question is hiding in the soil of the celestial body. So it happened that Curiosity was once again busy taking a sediment sample from a former Martian water body about 7 years ago. In the process, the rover was supposed to bring to light a mysterious grayish powder whose chemical composition immediately caused big questions for experts. In detail, the sample contained almost 75% silicon dioxide, a circumstance which is anything but usual for the actually basaltic crust of the planet. The researchers were no less surprised by the fact that the silicates also contained over 15% monoclinic tridymite. Typically, Tridymite is formed when silicates are strongly heated and then rapidly cooled. This special form of quartz is also extremely rare on our earthly home. So far, it can only be traced at 2 volcanoes in Japan and elsewhere in Greenland. The fact that the Gale crater, which Curiosity has been examining since its landing, does not harbor any volcanoes and silicon-rich magma seems particularly strange. In addition, we should not forget that the sample was taken from the bottom of a dried lake. In order to track down the origin of the inexplicable sample, the experts played through all possible background scenarios. In the end, the experts came to a surprising conclusion. The tridymite probably originated from a distant Martian volcano. Its magma remained in the chamber longer than usual, causing it to cool in places. As a result, components that had already crystallized sank to the bottom, allowing lighter, more silicate-rich components to rise to the top within the magma mixture. When the volcano finally erupted, mainly the upper, silicate-rich components were then ejected. The ash released during this explosive eruption was subsequently transported by the wind to Gale crater. Chemical analysis suggests that the lake, which has since dried up, was still holding water at the time. What at first sounds like a rather banal case of volcanic ash on a lake bottom actually holds significant potential for insight. Accordingly, the research results indicate that the volcanic activities of the Red Planet were much more diverse than previously suspected. Can we prove our reality in tiny particles and predictable structures? If so, we would have to venture into the world of electrons, neutrons, and protons. In the previous century, German researcher Werner Heisenberg claimed that it was impossible to observe these areas of life. The electrons appeared to behave too irrationally in his research. Heisenberg therefore defined a limit to predictability, measurability, and order, which later went down in the history of natural science and physics as Heisenberg's uncertainty principle. Today, much has changed, and new scientific approaches are enabling discoveries that are once again revolutionizing our view of the world. The subatomic realm is where what we see as our reality, as the Earth, as the universe, or even as a tree outside our front door, comes into being. Our bodies are made up of subatomic particles, and every word we speak or every thought we have shapes and moves this world of tiny particles. If we can explore and possibly control this world, or at least understand it first, we may hold the keys to shaping reality in our hands. In 2023, 3 researchers dedicated to exploring the subatomic world were awarded the Nobel Prize by the Swedish Academy of Sciences in Stockholm. Physicists Pierre Agostini, Ferenc Krauss, and Anne L'Huillier had been working on researching the apparent limits of unpredictability. To do this, they used light pulses in the attosecond range, which flash so briefly that their size is as incomprehensible to our minds as the irrational world of electrons. Attosecond flashes of light, electrons go crazy. Put simply, attoseconds are extremely small units of time. Attosecond physics is a new field of physics that aims to shed new light on the world of the smallest particles. If we really want to understand reality, we need to know how this world works. The subatomic realm is the web of matter. It is where all things, all forms, and all phenomena of our lives, including ourselves, originate. If we can find the functions of matter there, the blueprint, then we should also find clues as to who or what builds this world and where aspects such as liveliness, intelligence, and evolution come from. How can attoseconds help here? An attosecond is 1/billionth of a billionth of a second. Numbers like these are difficult for us to imagine, but let's draw a comparison. Within 1 second, as many attoseconds pass as there have been seconds since the universe came into existence. The realm of electrons is determined by these extremely small units of time. Electrons, charged with a negative electric charge, dart around in an incredibly large void and orbit a central point. Together with this point and other particles, electrons form atoms. The movement of electrons also gives atoms a charge and allows them to bind to other atoms, forming molecules. Molecules produce elements, and these build our world. Attosecond flashes can be used to make electrons visible, similar to a particle accelerator. While particle accelerators use collisions with incredible force to make particles observable for a short time shortly after the collision, attoseconds only simulate the electrons for a brief moment. Attoseconds only stimulate the electrons for a brief moment. This stimulation causes a change in the behavior of the electrons, and this change provides information about the true nature and physical behavior of the electrons. Atoms, electrons, photons, and other particles are so tiny that researchers could never see them as things or real particles of matter, even with the best microscopes. They can only observe the effects of these particles and then describe them. When the particles are moving in their natural paths, they are virtually invisible. When researchers apply a deliberate and controlled stimulus, the deviation from the normal path of the particles becomes briefly visible, and with it, the nature of the response to the stimulus. From this response, researchers can draw conclusions about the function and elementary behavior of the smallest particles, which in turn allows conclusions to be drawn about the structure of the universe and the forces at work in the subatomic realm. As you can imagine, this is work that requires patience and special technologies. The ultra-short light pulses of attosecond physics exert influence patterns on the subatomic world. Thanks to meticulous measurements made possible by computers, scientists can map the dynamics of electrons in atoms, and these findings have revealed a shocking picture of reality. Nobel Prize, Anne Lhuillier, Pierre Agostini, and Ferenc Krauss. Only the best researchers of our time receive the Oscar of Science. When the Swedish Academy of Sciences awards its prizes to the world's best researchers each year, it's not only the best in their disciplines who are honored. In most cases, the award also ensures that cutting-edge knowledge, new areas of research, and groundbreaking discoveries are brought to the attention of a wide audience. Before the Nobel Prize was awarded in 2023, probably no one had ever heard of Anne Lhuillier, Pierre Agostini, and Ferenc Krauss. After the winners were announced, the three researchers became famous overnight. Each of them has made significant contributions to attosecond physics in their own way. Anne Lhuillier invented a technique in which infrared laser light is passed through a noble gas, creating an overtone of light radiation in the attosecond range. Pierre Agostini developed a method of serial or train pulse technology, which he calls RABBIT. RABBIT stands for reconstruction of attosecond beating by interference of two photon transitions. The researcher generated a sequence of extremely short attosecond trains by passing a strong infrared laser through a noble gas. A further process known as highly harmonic generation produced high-frequency, ultra-short UV pulses. These pulses lasted only about 250 attoseconds each, and occurred at such regular intervals that the invention could be successfully used for test series in the field of electron research and imaging. Agostini also used a synchronized laser pulse in his own research to measure the interference between two photon transitions. These interferences enabled him to reconstruct the temporal course of electron motion precisely and with attosecond resolution. His approach made a decisive contribution to the first almost perfect temporal resolution of electron processes in atoms. Ferenc Krauss was honored for his pioneering work in the generation and measurement of individual attosecond light pulses. The Hungarian-Austrian physicist succeeded for the first time in generating isolated flashes of light that are short enough to capture the movement of electrons in real time. Like his colleagues, he used a strong laser pulse that was sent through a noble gas, generating so-called high-frequency harmonics. The spectral superposition then produced a single attosecond pulse. Using specially developed measurement methods, the researcher was able to determine these pulses so precisely that exact time resolutions in the range of electron movements became possible. Thanks to the work of the three researchers, it became possible for the first time to directly observe the fastest processes in matter. Today, scientists around the world are conducting research with attoseconds, revolutionizing our knowledge of the world of elementary particles. Attoseconds shape reality. Let's take a journey into the depths of matter, where our senses have long since failed us, but where reality emerges. Thanks to attosecond research, we are gaining insights into this mysterious realm and the fantastic life of electrons. The movements of these particles determine whether an atom binds or not, whether light is absorbed or reflected, whether electricity can flow, or whether a molecule is formed. To do this, they interact in specific patterns, use forces or generate them, build bridges, form bonds, or break them down again. All these movements take place on an incredibly short timescale. These tiny movements, performed billions of times per second, turn dead matter into living cells and chaos into order. They create everything that exists out of nothing, and it is the great challenge of research to find out where these processes come from and whether they are intelligently controlled. The attosecond is the unit of time at which our universe is constructed in real time. Those who understand this timescale not only see how the world is, but also how it's literally created out of nothing. If we gain knowledge and control over this dimension, we can begin to not only observe reality, but also shape it to a certain extent. By using targeted light pulses, electron trajectories could be influenced, which would mean, for example, that chemical reactions would no longer have to occur purely spontaneously, but could be controlled. Initial approaches have already shown that molecules can be steered in their behavior if they are hit at the right attosecond moment. This is a direct intervention in the formation of matter itself. Technologies that still sound like science fiction today could soon become reality. The manipulations could be used to manufacture new materials, control biological processes, or develop ultra-fast quantum computers. The biggest challenge at the moment is still precision. In these incredibly small units of time, any disturbance, or even the slightest noise, can tip the balance into unpredictable chaos. We need to understand these mechanisms even better if we no longer want to accept reality as a given, but want to actively shape it. Research, such as attosecond physics, takes us to the boundary between science and metaphysics. For what happens when we can not only observe, but also decide when something happens, or whether it happens at all. We become creators on another level of reality, and thus, in a sense, what religion calls God. Is matter really real? It seems so. When you put your plate on the table, it stops, and you can take the food into your body. You will notice that this act has an effect. You hear your digestion and gain strength through the food. There is no question that the world of matter exists somehow. We can kill ourselves with weapons, or rather destroy our bodies in the material world. But recent studies show that the world of matter is nothing more than a hollow projection created for us to experience. As protagonists in this world, we may be far more than we appear to be. We may in fact be something quite different from mortal bodies with a brain and a heart. So far, scientists say that when the body is destroyed, the human being dies, and quite a few scientists claim that this must definitely be the end of life and existence. But there is evidence that our bodies are just condensations within three-dimensional space, possibly controlled by what religious people might call a soul. Similarly to Avatar, we could simultaneously exist in another world, sleep there, and dream our lives as avatars on Earth. Then this world here would be nothing more than a puppet show. In a way, we ourselves are players and protagonists, but most of us are not aware of this. The theory of relativity is not the measure of all things. Was Einstein wrong when he proposed the theory of relativity? Some modern theories, such as quantum gravity and string theory, call his assumptions into question. The theory of relativity does not work on a microscopic scale. Quantum physics and relativity often contradict each other. There must be one or more levels that unite the two. There is no other way, because quantum theory is the theory of the world of the smallest particles, the quanta of light, and these are the building blocks of all large phenomena. Einstein's theory of relativity refers to the universe as space, to stars, planets, and the effects in the world of visible objects. But these objects are all made up of light quanta, and they do not behave as if matter is real. Einstein's theories remain fundamental, but science is evolving. At the moment, we are at a point where this type of physics is no longer getting anywhere. The latest discoveries of the James Webb Space Telescope can no longer be described with the old physical theories. Einstein's concept of space and time must have been incomplete. Quantum mechanics reveals phenomena that his theory does not explain. Black holes and singularities contradict the general theory of relativity in some important points. The existence of dark matter and dark energy remains a mystery. Space and time might not be fundamental quantities, but much more flexible than previously assumed. The connection between gravity and quantum mechanics is also still unclear. The latest findings show that gravity may not actually be a force, but rather a curvature of space-time caused by masses and energy. Some scientists suspect that space and time itself could consist of tiny, quantum-like structures. These structures could behave in ways that we do not yet fully understand. They may possess some kind of intelligence or represent some form of force or life that we could not yet imagine. There is evidence that the physical forces in the universe have changed over time, which would suggest that the universe is undergoing some kind of evolution that resembles life. Einstein's work is a milestone, but the search for a unified theory continues. However, if it turns out that the universe is just as changeable, a hollow projection as we are, we have a poor chance of approaching the truth with the old methods of physics. Then we will need superperception or completely new branches of science to unravel the mystery of the cosmos. How does hollow projection work, and who creates it? So, if everything is just a hollow projection, where does it come from, and how is it structured? The idea is essentially based on the concept that all the information that creates our three-dimensional universe could be stored on a two-dimensional surface. This theory has its origins in quantum mechanics and the general theory of relativity. Quantum mechanics discovered that quanta are nothing more than information carriers that are incredibly changeable. They can become a table and thus convert the information of a table to planet Earth, or they can become any other matter. But even if they form themselves, they have the fascinating property of immediately dissolving their form again if they are not measured or observed. In quantum physics terms, this means that your table disappears when you or nobody else is looking. Hollow projection theory assumes that our three-dimensional universe is just a fairly loose projection of information stored on a two-dimensional surface. The idea originates from physicists such as Gerard Hooft and Leonard Susskind, and was first introduced in the late 1970s. The decisive factor was the observations made in the vicinity of a black hole, which showed that the amount of information contained in a certain volume of space is limited by the surface of this volume and not by its volume itself. This contradicts the classical understanding of information and space, and could mean that the spatial dimensions themselves could be wandering phenomena controlled by deeper physical levels. In practical terms, this would mean for our known universe that every piece of information required to construct and maintain this projection is theoretically stored on a two-dimensional surface at the edge of the universe. This information is then projected in such a way that a three-dimensional space with material objects and physical phenomena appears optically. A universe of pure consciousness? Our brain plays another key role in this scenario. We can only perceive the world and the universe through our brain and our senses. We basically do not see what is really out there. We only see what the brain lets us see. In the holographic universe, gravity is a result of the projection of information from the two-dimensional surface. This means that gravity is not really a force in the traditional sense, but a dynamic property of the holographic projection. In a holographic universe, we play an essential role as conscious observers. We could be experiencers and creators in equal measure. Now, it has not been scientifically proven that a table really disappears when nobody is looking, nor can we monitor this in an experiment because the camera with which we observe would be equivalent to a measurement that maintains the shape of the table. Another exciting idea in this context could be the role of consciousness. Scientists don't really know what consciousness is yet, but it's certainly instrumental in shaping quanta from the wave to the particle state. Now, it could be that the whole universe is infused with a kind of consciousness that shapes and sustains it. Our consciousness is only a part of the greater whole of consciousness, and we are co-creators. But we don't have to worry about the table remaining a table, for example. Is the speed of light the problem? Do you remember from your school lessons that the speed of light is the measure of all things in space? Einstein spent his life researching the forces and phenomena in the universe, and came to the conclusion that all phenomena and forces are dependent or relative to each other. Time is dependent on the location of the observer. Acceleration influences time, and the speed of light supposedly sets absolute limits. But this could be a mistake in our physics. If the nature of light is possibly completely different from what we have imagined so far, this could mean that all our observations and conclusions of the last 100 years are wrong. The light we see is quanta, and we now know that they behave very capriciously. So how can the speed of light be a stable measure? It's possible that we have created limits for ourselves through this view and constructed a false image that we now need to revise. In reality, light could be much more dynamic and changeable. But what would that mean in relation to our observations of the early universe? If the speed of light were indeed variable, we would have to completely rethink our models of cosmic evolution. The observations of the cosmic background radiation that have so far provided us with information about the early universe are based on the assumption of a constant speed of light. Variations could mean that all our calculations of distances and times are wrong. Then our estimates of the age of the universe and the speed of its expansion would also be wrong. This could explain why the Webb telescope shows us galaxies that are so old that they shouldn't even exist. We normally measure the age of galaxies using the redshift of light. When the universe expands, the light is stretched and changes to a reddish color. However, if the speed of light is not constant, our measurements of the redshift are also incorrect. Ultimately, however, this does not mean that Einstein, Hubble, and all the others who built up our cosmology were frauds. They just delivered the best possible work and explanations for their time and era. They seemed to work very well for almost 100 years. But now it turns out that these theories are incomplete, and we need to open up our science to new dimensions of truth. We could possibly explore a holographic universe only through our minds, but we still have to learn the techniques to do so. Think about it. In the 1970s, there was a man with supernatural sensory perception who could only examine Jupiter through his inner spiritual vision. Ingo Swann's work is often hushed up today, but Swann described the planet's atmosphere almost perfectly and even saw its fine rings, which were only discovered by the Voyager 1 probe in 1979. Before we become such superbrains, the age of quantum computers will probably dawn. These extremely powerful computing machines should, among other things, help us to better understand the true nature of the universe and show us where our previous mistakes lay. Click on the subscribe button now and be part of every new video.